Good morning, class. We're going to start our next module of the 4220/5220 course, and we're now going to look into cooling towers a little bit. FYI, there will be another homework assignment coming your way shortly, and there's also a link to not only this presentation I'm recording, but also another one about 18 minutes, something like that, on the use of variable frequency drives to control cooling tower fans, which is really quite good. I just found it a minute ago, and I think you'll enjoy both of these. Okay, I will also email out this presentation as you do not yet have a paper copy of it. Okay, so I have shamelessly stolen this. It was posted online, and I came across it a number of years ago, and I like the presentation quite a bit. So while I'm not 100% on all of these slides, I think we can make it through, and it's a pretty good introduction to cooling towers. Okay, so this is the agenda, so we'll go into the introduction first. And this slide simply shows a little bit of a generic picture. We'll get more specific types as we go forward in the presentation, but this is basically what a cooling tower does. We have some sort of a heat load, which we're showing this heat exchanger over here, which typically is a chiller. In industrial processes, it could be an industrial process that requires cooling, something that's generating heat that the equipment, simply can't function if it's not provided cooling water flow. But, in an HVAC application, we usually think of this as the condenser on maybe a large centrifugal chiller. So we're pumping cool water, which is initially in the basin, has already been through the tower and is cooled down. Design numbers are typically, at least in the old days, have been 85 degrees coming out of the basin and 95 degrees coming out of the chiller being supplied to the top of the tower. Once at the top of the tower, the water is distributed out in troughs. Different ways of constructing those. We have some nozzles. Sometimes these are just holes. Sometimes they're actual nozzles which spray the water out. Usually we have a fill material in here that the water is sprayed down upon or falls into to increase the intimate contact with the air that is either blown in a forced draft situation or sucked in an induced draft situation. The fan can be on either side. We'll talk about that. We get some evaporation, which causes the cooling of the water stream as it goes through here. A little bit of straight convection, but most of the cooling is by evaporation. It's possible to throw droplets, that's called drift and windage, out of the tower. We have some mist eliminators on the path to try to keep this down to a minimum. And then, of course, the water falls back down, having been cooled into the basin. Now, we are constantly evaporating water. That's our cooling mechanism. And so we have to make up water. And so this makeup water is going to have minerals and that sort of thing in it. So we have to blow down some water because these minerals would continue to concentrate to the point that we scaled up the tower, and then we would lose tremendous performance. So you have to maintain your water chemistry pretty closely on a cooling tower. And so we have a blowdown. We're showing a flow meter, which would be a best practice to actually measure the amount of blowdown flow. We are injecting some chemicals because these things can, it's fairly warm in the summertime. It can grow algae and all kinds of stuff that you don't want. And so we put some chemicals in here to keep that from happening. And we also want to meter the water flow to the tower by tracking this over time, you can make sure that your tower is functioning properly. And it's just good management to know how much water you're making up and how much you're blowing down the drain. Obviously, the more you blow down to control this water quality, the more you have to make up. So the makeup water is the sum of the evaporation, the windage, everything that leaves the tower as possible for the sump to overflow, and then whatever's blown down on purpose. Okay. So we're going to look at these various components. You know, there's a frame, structural members that hold this thing up. And depending on the type of tower, there's different ways that they can be constructed. That's not our particular focus, even though it's part of the device. And then, of course, I mentioned the fill on the previous page. That's these days it's mostly plastic in different configurations in order to break up the water either into small droplets or to cause it to create a film. There's splash type fill and film type fill that we'll talk a little bit about. It turns out that in most cases the film fill is actually a little more effective. It's possible to retrofit a tower if the fill gets torn up over time, ice and chemicals and things like that, and just structurally it can break. It can be taken out and replaced. I mean, it's a fairly big job, but it can be done, and you can upgrade a tower from, say, a splash fill to a film fill, at least some of them. You have to check with the manufacturer to see if that's possible. If you do that, you're probably going to get better performance out of the tower than it was initially designed for. And we talked again previously a little about the cold water basin. It's at the bottom of the tower. They oftentimes in colder climates will have heaters to make sure that we don't form ice and freeze this thing up in really cold weather. They're typically electric resistance heaters, which are fairly expensive to operate. It would be possible to use steam or hot water or some other heating source, but because of the fairly remote location of cooling towers, often they are typically electric. Okay, additional components, drift eliminators. They're as after the air comes out of the fill and is traveling usually vertically up through the tower, someplace along the way. Can be right at the exit of the fill, or it can be further up in the tower. They have these. They're really kind of like louvers. They're kind of they go back and forth, and they make the, hopefully as the air with the droplets flows through them, the droplets will impinge on these louvers, and then they will stay in the tower. They will drop out of the airstream. They're pretty effective, so that's just a mature technology. We have an inlet. Most of the time it's on the side of the tower. It can be the bottom where the air comes in. Louvers are used in induced draft cross-flow towers, as we'll see quite a bit, to just kind of equalize the flow of air into the fill and across the fill, and to make sure that's done kind of in a balanced way. Nozzles we talked about, that's up at the top of the tower to distribute the water into the fill. And of course we have fans to move the air through the tower. Some towers are called forced draft fans, and we'll have centrifugal fans down at the base or on the sides that blow air through the tower. Other towers are called induced draft, and they have typically axial propeller type fans mounted in the top of the fan, and they blow air out the top, and so they induce or suck air through the cooling tower. So we'll see a little more about that as well. Let's see, so we'll move on to types of cooling towers now. Okay, so there are natural draft type cooling towers. These are typically at large power plants, some large industries may have them. That's the kind of parabolic shape you'll see in a minute. That's what a lot of the environmentalist people brand as pollution. It's really not polluting anything. And in fact, the parabolic towers don't even have fans, so they're extremely environmentally friendly. They do reject heat. Typically nuclear plants have these things, where fresh, cool air is drawn in the bottom of the tower, no fan, concrete. The sides of the thing built kind of in the shape of a parabola, or can be up to 200 meters, which is somewhere in the order of 600 to 650 feet tall, which is pretty darn big. And it's large heat duties. These things are extremely expensive. A nuclear power plant, it's worth it because you have to move so much air to, condense. It's for the condenser in the Rankine cycle. And the fans would be huge, and the energy to drive the fans would be very large. So in those cases, they're willing to invest in these natural draft cooling towers. Okay, so they have two different configurations. There is a cross flow, which looks this way, so the air comes in the side, as you can see over here on the cross flow, and then comes across the fill this way, and then turns and goes up. We have warm, moist air in here, and we have colder air out here, and so just the density differences causes this to circulate, and so we don't need a fan. And so you can look at kind of the configuration, but basically it's like the parabola, the reinforced concrete shells. Looks like it's not supported by the fill, but it looks like it's sitting on top of it, and you've got your cold water collection basin at the bottom. And then here is the counterflow. It's like the fill is kind of jacked up a little bit, and the air comes in and then goes vertically through the fill instead of kind of sweeping across the fill. And I don't know all of the details on the design preferences between these two. For our purpose, I just want you to know that they're out there. You see the drift eliminators, and then the counterflow. I don't believe they show them in the cross flow tower. But so that's, the little louvers that kind of divert the airflow a little bit back and forth, and hopefully any droplets will hit one of those and just fall back down and stay in the tower and not be carried up through as a loss out the top of the tower. Okay, moving on. So now we have what we call mechanical draft, which means we got a fan to move the air through the tower. So if it's a big tower, we can have large fans. I know the TVA Magnolia combined cycle plant has 3 generating units. They have 3 cooling towers. Each tower has 5 cells, and we'll see more what that means, but each cell has a 200, I believe it's a 200 horsepower motor. So what is that? 200 times 5 is what, 1,000? That's 3,000 horsepower. If I can do math in my head here quickly. It's a lot of energy. And one of the recommendations for that plant is to go to variable frequency drive speed control to reduce the fan energy cost. Anyway, let's see. So water falls over fill surfaces to get us the maximum heat transfer. We got lots of different things that affect the performance we'll talk about. And you can group these cells together into one large tower, and each cell will have its own fan. So we'll see. The types, there is forced draft, where you have the fan basically blowing the air through the tower. That's almost always a centrifugal fan. I guess it can be a propeller, but most of the time, because you have fairly high pressure drop when you blow the air through the fill like that, it requires a centrifugal fan, which is less efficient at providing the airflow than the induced draft type fans. That's why forced draft towers are not as common. Most of the ones you see are induced draft. Sometimes because of space limitations and this, that, and the other, you can put a forced draft tower in where you cannot fit an induced draft tower. And then we'll see on the induced draft towers, there's cross-flow and counterflow. We have similar meanings to the natural draft towers we just looked at. Okay, so here is a little diagram of a forced draft cooling tower. We're showing a centrifugal fan, which is pulling in air from outside the tower, and it is basically blowing it vertically up through the fill as the water falls down. We see we have nozzles up there spraying the water, distributing the water into the fill, and then we have drift eliminators up at the top. The basin is down low where the cold water accumulates and then is pulled out by the pump to circulate it through the heat load. So advantages suited for high air resistance, and fans are relatively quiet, even though they do tend to use more power per unit of air moved than the propeller fans. And so I would say that is a disadvantage. And what they really talk about here is recirculation. So what that is the air coming out the top of this thing out here where these little squiggly arrows are lined up is typically saturated. So the relative humidity is 100%. And so this air can't hold any more moisture. So you can't, and because the high velocity is down here in the center of the tower at the blast of the fan, it's relatively low up here. And so it's possible, and this fan is sucking in down here. So if some of this air recirculates down and gets pulled back into here with all that moisture, you will decrease the performance of your tower. So recirculation is kind of a big deal in towers, and I'll have some handouts and stuff. We'll talk a little more about it. But because of the low velocity, we'll see the induced draft towers have a much higher, like, I don't know, 3 to 4 times the velocity coming up here because the fan is up here instead of being down here at the bottom or over on the side, blowing up through the thing. And so it's much easier to get recirculation with a forced draft tower. And so that is a major downside of them. Okay, moving on to induced draft towers. Like we said, there's 2 types, cross-flow and counterflow. One advantage is that you're much less likely to have recirculation than the forced draft towers. And disadvantage, though, is that the fans, the motors, the motor drive is typically in that moist airstream, and it can lead to significant maintenance failures. It's got to be well weatherproofed, and so it's just an issue when you have that type of equipment in that moist airstream continually. Okay, so let's look. This is the induced draft counterflow, and so we're showing 2 pictures here. The one on the left doesn't have a fill, which I don't know that I've ever seen a cooling tower without fill. This picture indicates that they do make some, so this information. So the induced draft, we see the fan up at the top, which is blowing with a high velocity, blast out the top of the cooling tower. And so it induces or sucks the air in the sides through those louvers. And the louvers are there to kind of distribute the air and make sure that we get it into the tower in a fairly uniform fashion. Let's see, hot water enters the top, air enters at the bottom and exits the top. Uses forced and induced draft fans. This is an induced draft tower we're talking about, so I'm not sure what that comment's about. But anyway, so I think you get the idea how this will operate. Okay, and let's see. So, okay, so this is the counterflow, and so the air comes in, but it turns vertically, and then it's going vertically through the fill while the water is falling down the other direction. So that's why it's called counterflow. This is the crossflow, and you see it's a similar situation. We have the propeller fan, the axial fan in the center, blowing up out of the top of the tower, inducing the air across the fill. This time the air kind of flows in a horizontal fashion, so it's across the flow as the water falls down. So a little bit of a different configuration. We see the drift eliminators. We're showing those guys, these little curly things. That's kind of what they look like. They're just long, kind of curly slats like that. And then as any droplets hopefully will hit one of those things and fall back down into the tower. The water is entering the tower, is distributed to these basins up on top, and then they fall down. This type usually just has holes. They call them nozzles, but they're holes on a regular spacing. And we have to have our flow rate correct into these basins. It's the head. We want a certain depth of water that we want to maintain in order to give enough pressure so that this water comes out with enough force that it spreads out and keeps the fill uniformly wet. I guess that's this double flow is what you usually see. I get these are much smaller, obviously, and I don't recall seeing a bunch of these, but I may have and just not paid much attention to the actual internal designs of it. Okay. All right, so let's go on to assessment of cooling towers. So my goodness, we've got a lot of things to talk about here. If you're going to take data and try to figure out how a particular tower is operating, and this could be also from a design point of view, where you have to, select these parameters for tower selection. But the key parameter for tower performance is the wet bulb temperature of the air. That is, the wet bulb is the theoretical minimum water temperature that we could ever get out of an infinitely sized tower. The dry bulb temperature of the air, the cooling tower inlet water temperature. Is this an HVAC application? Is this an industrial application? Typically HVAC, like I've said, we see 95 into the tower and 85 out of the tower. Some designs these days are trying to minimize the condenser water flow, and so to save energy, and so they may upsize the tower and have a lower flow with a higher temperature. So, you can transfer the same heat with less flow if you let it get warmer, but of course then you have to make sure that the chiller manufacturer is good with that as well. Anyway, the inlet water temperature, the outlet water temperature, how many degrees do we need this tower to be able to cool the inlet water on the highest wet bulb temperature day of the year. That's of interest. Exhaust air temperature, electrical readings on the pump and the fan motors, the water flow rate and the airflow rate. Those are all important parameters to know. I threw a site chart in here because anytime you have a device where you have to know wet bulb temperature of the ambient air, sometimes, I mean, you can measure wet bulb, but a lot of times we just have relative humidity. And I don't know if you're up on your site chart. I would hope you are, but you can see that these are lines of relative humidity. These down here, these are lines of dry bulb temperature, and the lines of wet bulb temperature are over here, and they sweep down across. So if any two parameters will let you determine a wet bulb temperature if you don't know it. So probably temperature and relative humidity are the most common. So anyway, we'll be using a site chart a little bit, we'll be using a site chart a little bit, some of this, which is a good thing. All right. So, okay, so the performance parameters on a cooling tower, we're going to go through all of these different items. We've got a slide or two on each one of them, so let's get on about it. Okay, so the range of a cooling tower, as illustrated in the little figure, is the difference between the hot water temperature in and the cold water temperature out. Okay, so how many degrees did the tower cool down the water from when it came in to when it left? That's the range. Okay, so, you know, for a given water flow, if you make the tower bigger, you can get the water cooler, okay, because you have more airflow for a given water flow and you get, you know, better performance. So better performance is more delta T, you know, at a given wet bulb, dry bulb, for the ambient, okay? So high range equals good performance, okay? Approach. And so, you know, what the approach is you look at the difference between the cold water temperature out and the wet bulb. Because remember, the wet bulb is like that's the lowest temperature we could ever even theoretically achieve with cooling tower operation, because it's an evaporative device, and once you have cooled to the wet bulb, you've saturated the air and that's it. And so you can't go below that. It's because of the evaporation. And so the closer you can get to the wet bulb, the better it is. And the bigger tower that you bought, a tower, you know, for a given application, you can accept a larger approach and buy a smaller tower and get out cheaper on the front end. However, if you want your best performance, you want, you know, colder condenser water to help your chiller, then for a given heat load and wet bulb temperature, you have to buy a bigger tower. So that's kind of what a low approach is. Good performance. You know, you got a well-sized or a large tower relative to your application. High approach is not good. Either it was not selected right, or the tower could be scaled up, or, you know, the fill in bad condition, some of it's collapsed, or the fan's not blowing air right, or, you know, you got a problem. So if your approach goes up, then that's not good. If your approach is at design or what you expect, then it probably means your tower is operating pretty effectively. Okay, tower effectiveness. It's just a performance parameter that we can calculate, that you can do it on the same tower over time. If you have this on data acquisition, you could have this automatically calculated and stored and plotted and track it over time. How effective is the tower? So that's the range, which is the cooling that we get divided by the range plus the approach. So range plus approach is the difference between the hot water temperature in and the ambient wet bulb. So real simple to calculate. High effectiveness equals good performance. And I put down there at the bottom, if you had a tower of infinite size, the range would be the inlet water temperature minus the wet bulb temperature. So with infinite size, we can cool the water all the way to wet bulb. It's just those things cost a lot of money, those infinite towers. Okay, cooling capacity of a tower, heat rejected in BTUs per hour, or you can use, you know, other systems of units, or tons of refrigeration. And let me just remind you that a ton of refrigeration it doesn't mean just a whole bunch, it means 12,000 BTUs per hour. So a ton of refrigeration is a rate, and it's 12,000 BTUs an hour. And of course, you can calculate, you know, the amount of refrigeration that we're getting. Sorry, I got something in my mouth. By the mass flow rate of water times specific heat times temperature difference. So m dot Cp delta T or m dot delta H. So, you know, high cooling capacity equals good performance. Okay, evaporative loss. And these slides initially came in metric, and I've translated most of it, but I've not taken the time to fight my way through the conversion of this equation. It's not very hard, I think, but I just have never done it. So I still haven't done it. So we can, there's an evaporation loss. I mean, that's the purpose of the cooling towers, to evaporate some of the water falling through it to cool down the rest. And so theoretically, it's about 1.8 meters cubed for every million calories of heat rejected. And a million calories is just short of 4 million BTUs. That's like 3,900,000 and something thousand. So that's almost. So, and a meter cubed in terms of gallons is something like 220. So it's like 220 gallons of evaporation will cool about 4 million BTUs of heat rejected. And you got a little equation there. If you're working in the metric, you got to put in your circulation rate in meters cubed per hour, your temperature difference in degrees C, and then you can calculate that. So I don't have that. Well, I've got another presentation that we'll go through that I think has this in US units. So anyway, we can calculate. If we know how much heat we're rejecting, we can pretty well calculate the amount of evaporation loss it's going to take to do that. Then there's a term, cycles of concentration. This is cooling tower lingo. It's the ratio of the dissolved solids in the circulating water, which is going out to the chiller and back, to the dissolved solids in the makeup water. And so that's going to be higher than your circulating water because your makeup water should have been cleaned up some. But we'll see. And then there's also blowdown losses. And this depends on the cycles of concentration and the evaporation loss. So the blowdown loss is the evaporation loss divided by the cycles of concentration minus 1. So we'll get into these numbers some later and in other presentations. So right now I just want you to at least read the definitions and have heard the terms. Okay, also a parameter that's important in cooling towers is the liquid to gas ratio. And so L, it would be the mass flow rate of the liquid divided by the mass flow rate of the gas. So, you know, the liquid is the water falling through the tower, and the gas is obviously the air that's being blown up through it in order to cool it. So, so L over G is the ratio of those mass flow rates. Heat removed from the water must be equal to the heat absorbed by the surrounding air, just a heat exchanger. And so the L would be the flow rate, the mass flow rate of the liquid, CP specific heat, temperature in minus temperature out is equal to the mass flow rate of the air times the enthalpy difference in and out. And so you can see if you measure those parameters, of course it's hard to measure an enthalpy, but you can measure a temperature and relative humidity and calculate an enthalpy on the air side. And so you can, you know, if you get all those 4 parameters and know the specific heat, you can calculate the L over G ratio. The cooling tower manufacturers, they obviously go into great depth and detail, and they design a tower around a specific range of L over G ratios. Okay. Energy efficiency opportunities. We'll look a little bit into this. Well, you know, let's select the tower right. So we'll go on into that. Capacity. How much heat do we have to dissipate? BTUs per hour. BTUs per hour twice, whatever. We're going to have to work on this presentation a little bit before I send it to you. So, that comes from the process. What is it you're cooling? I mean, is it a condenser on a chiller, or is it a bunch of industrial processes? You've got to go and figure out how much heat you're going to have to reject. And then that's one of the basic parameters for tower selection. Circulated flow rate in gallons per minute, GPM. So we know how much heat, and we know how much water we're going to circulate. So that's going to tell us how much temperature drop we need across the tower, which helps us size the tower. And there are other factors. Okay, so we have to determine the range. Range is determined by the process, not by the system. Required process water supply temperature, flow rate, amount of heat. So all that has to be juggled. Approach, if the closer we get to the wet bulb temperature, the bigger the cooling tower has to be, and more expensive. One thing you can do for a given heat load, if you upsize the tower, you can get by with a smaller tower fan, and so you can downsize the horsepower of the motor. So, and that's going to save energy over the lifetime of the tower. So that's something to consider as well. Okay, heat load. This looks like it's redundant. Okay, anyway, wet bulb temperature considerations. Water is cooled to temperature higher than the wet bulb, we know that. So the leaving water temperature is the wet bulb plus the approach. Where are we going to put this thing? Are there other towers around? We don't mention interference here, but if you already have some cooling towers, you don't want the blast from those cooling towers being pulled into the inlet on a new cooling tower, because it's going to have higher moisture content than you expect given the climate and the surroundings. And so that's called interference. And then, of course, recirculation. We're concerned about the prevalent wind conditions and directions and all that sort of thing. Make sure we're not blowing this blast up against a building that won't let it escape, etc. Things like that can happen. If you expect some recirculation, you have to upsize the tower to make sure that it can handle it. Okay, that's pretty good. Okay, what type of fill media? Like we said, the film fill is a little more efficient than the splash fill. I would suspect that these days that's what you would probably be looking at. But we know the hot water is distributed over the fill media, cools down through evaporation. Fill media impacts electrical use. If it's more efficient, then we don't need to run the fans as much. We can get away with less water being moved, etc. Here's a comparison, and I've not translated this from the metric either. We see different different L/G ratios. We see effective heat exchange area, meter squared per meter per volume of fill. So we see is much greater for the film fill. Fill height required is smaller for the film fill. Pumping head requirement in meters, that's I guess that's because of the elevation of the tower. If the tower is shorter, you don't have much static head on the pump, and the quantity of air required is lower than the last two. So that all affects the energy use. Pumps, we'll talk more about pumps later. Water distribution, increase the cycles of concentration. By cooling tower water treatment helps reduce makeup water. The higher cycles of concentration, the less water that you're putting in. So there's a little bit of savings there. Drift eliminators, if you don't have them, you can reduce the amount of water blown out the top of the tower. Cooling tower fans, Obviously, they got to move air through the system, so they see the resistance, pressure loss. So if the fill has more resistance, that's primarily what you're coming through. And then it also has to pull through the water that's falling either in counterflow or crossflow. That will affect electric use. Depends on blade profile. There's replacement of metallic blades with FBR blades. They're quoting some savings. I'm not really familiar with that. But you want to use the most efficient fan blades that you can in order to decrease that energy requirement. And these days, we're seeing a lot of conversion of tower fan control from start-stop or two-speed motors, shifting rotational speed to just variable frequency drives. Saves a lot of energy. That's major retrofits are going on across the country, across the world. They also, the VFDs, they save a lot on maintenance, because if you've been running start-stop, you're starting to stop in that motor, hundreds of times a month, and it just causes things to fail. And so the VFD can start and stop if it needs to, or just modulate speed. VFD starts and stops. It just starts just very slowly, winds up, and doesn't cause a problem on much of anything. And that's what the video link that I'm supplying with this will talk about. Okay, so thanks for your attention. And we have successfully made it through the introductory presentation on cooling towers. Thanks for your kind attention, and we will now end this and post it. So we will be back in touch soon.